So as I said, this is the last in the seminar series, which has been devoted to early career researchers who submitted papers to the Bachelor Centenary meeting and who were unable to present because of the constrained circumstances that we are all very well aware of. But we've had a very good series, and as I said, this is the last one, and it's my pleasure to introduce our first speaker for this afternoon, who is Wang Guohua. He's an associate professor in the College of Civil Engineering and Mechanics at Langzhou University in China, where he received his bachelor degree and PhD before working as a postdoc in the College of Engineering at Peking University, and he returned to Langzhou in 2016. His research is focused on high Reynolds number wall turbulence, gas particle two-phase flows, atmospheric flows, and aeolian transport. And he's going to talk today about very large-scale motions in the atmospheric surface layer. So, Guohua, over to you.
Okay, thanks for the introduction. I'm very honored to have the opportunity to give a speech at Professor George Batchelor's 100th anniversary meeting. I'm Guohua Wang. Hongyou Liu and Haihua Gu are my colleagues. Professor Xiaojing Zheng is my PhD supervisor. Zheng has introduced a wind tunnel study on the influence of sand particles on very large-scale motions in sand-laden flows in March. Today, the topic of my talk is very large-scale motions in the atmospheric surface layer. Okay, as we know, there are two types of turbulence structure in outer region of wall turbulence. There are very large-scale motions and large-scale motions. In 1970, the large-scale motions with streamwise length range from 1 to 3 times of the boundary layer thickness in the outer region of turbulence boundary layer were revealed. At the end of the last century, much longer mid-range structures named very large-scale motions have been evidenced in the outer region of high Reynolds number wall turbulence. Their streamwise length scale are larger than 3 times of the boundary layer thickness. So we can see that both the large-scale motions and very large-scale motions live in the outer region, especially in high Reynolds number wall turbulence, and they could be divided by their length. The max streamwise length of very large-scale motions can extend from 6 to 20 data. Data is the boundary layer thickness. In atmospheric surface layer, previous study has demonstrated the existence of very large-scale motions. In 2007, and they also known as superstructures. These structures are inclined along the flow direction. The inclination angles range from 11 degrees to 25 degrees under the neutral conditions. Studies have revealed that the very large-scale motions contribute more than a half turbulent kinetic energy and Reynolds stress in wall turbulence. Also, they play a very important role in mass transport, such as the dust transport in sandstorms. Zheng have pointed out the very large-scale motions dominate the streamwise transportation of PM10 in sandstorms. PM10 is a very tiny particle with size less than 10 micrometer. Our initial motivation for this study was to know how dust transport in sandstorms and how to predict the dust transport. For this purpose, Professor Zheng proposed constructing a field observation site, and it is now called Qingtu Lake Observation Array Site. The Qingtu Lake observation area site is located on the flat, dry, sandy bed of the Qingtu Lake, between Bananjaran Desert and the Tingle Desert in Minqing County. Minqing is in the northwest of China. The Qingtu Lake observation array is about 500 kilometers from Lanzhou in north direction. This area is on the pathway of the strong northwestern monsoon and the storms in spring. The altitude of Qingtu Lake is about 1,300 meters. The upwind area of the Qingtu Lake site is composed of two regions. Region B from 0 to 10 kilometers and region A from 10 to 30 kilometers from the site. In region B, the ground is flat and devoid of vegetation. The height variation is less than 1 meter. Region A is also devoid of vegetation, but has a few dunes. The dunes are about 2 meters high. There are less than 5 dunes per kilometer in the upwind direction. The minimum distance between two neighboring dunes is about 200 meters. It is 100 times of the dune height. The average of surface sand grain size is about 200 micrometer. The Qingtu Lake observation array includes 1 main tower and 32 low towers. The main tower is 32 meter high and the low tower are 5 meters in height. 10 of the low towers were arranged in the northwest direction and 10 else were arranged in the west direction with equal distance of 30 meters from the main tower. The remaining 12 low towers were located on the both sides of the main tower in the streamwise direction with equal distance of 5 meters. During the observation, wind velocity, dust concentration, sand transport, electric field, atmospheric visibility are measured synchronously. Here it shows the 3 components: wind velocity, temperature, 3 components of electrical field, and PM10 concentration in clean air flows. Also, the wind velocity, temperature, and electric field PM10 concentration during a dust event are shown in this figure. We can see that the PM10 concentration is much larger than that in the clean air flows. Because the flow condition is uncontrollable in the atmospheric flow, the measured raw data cannot be used in the further study without pretreatment. The pretreatment for the raw data contains stratification, stability judgment, wind direction selection and adjustment, and stationary wind velocity selection. Also, the detrending process introduced by Hutchins is employed to obtain the accurate turbulent fluctuations without synoptic waves. From 2013 to 2017, the observation lasted for more than 7,000 hours. High quality data is about 595 hours, including 422 hours of clean air flows data and 173 hours of sand-laden flow data. We calculated the mean velocity, turbulence, kinetic energy, and Reynolds stress in the clean air flows under the near neutral conditions. The statistics are consistent with the boundary layer theory. Therefore, we think the data can be used to study the very large-scale motions in the atmospheric surface layer. The shape of the very large-scale motions in clean air flows is analyzed. combining with previous studies, we found that the inclination angle of very large scale motions has no obvious change law with Reynolds number. Actually, the variation of inclination angle with friction velocity follows a near linear decrease in the neutral regime. This may be because there are large differences for boundary layer thickness in different experiments, especially between the ASL and the turbulence boundary layer. The boundary layer thickness may have no influence on the inclination angle. We found that the outer-scaled streamwise length, spanwise length, and vertical length increased with the wall normal distance. It agrees with the previous studies in lower Reynolds numbers wall turbulence. The variation of streamwise, spanwise, and vertical length with Reynolds number were also analyzed. We found that the outer-scaled streamwise, spanwise, and vertical length of very large-scale motions have no dependence on Reynolds number when the Reynolds number is larger than 2000. By low-pass filtering with a cutoff wavelength of 3 delta, the turbulence kinetic energy of very large-scale motions and their fractions are analyzed. We found that both the TKE of very large-scale motions and its fraction increase log linear with height. The TKE variation with height is different from the result in the turbulence boundary layer at lower Reynolds number. Next, I would like to introduce very large scale motions in sand-laden flows, including the influence of sand particles on the very large scale motions and the contributions of very large scale motions on the sand dust transport. High quality sand-laden flow and clean air flow data are adopted to study this issue. This table shows the flow parameters and of sand-laden flows. The average PM10 concentration profile is plotted, and it can be seen the PM10 concentration decrease with height. The percentage of PM10 ranges from the 0.5% to 5% at different heights. The average sand particle size range from 70 to 105 micrometer. Our measurements revealed there exist very large-scale motions in sand-laden flows. They have similar shape with very large-scale motions in the clean air flow. The structure inclination angle in sand-laden flows decrease linearly with the friction velocity. They are greater than the structural inclination angle in clean wind. Moreover, the structural inclination angle increases with sand concentration. We found the velocity gradient decrease with sand concentration at a similar friction velocity range. Previous studies have revealed the structural inclination angle is inversely proportional to the velocity gradient. It may be the reason why the angle increases with sand dust concentration. The decrease velocity gradient is a decrease of the structural inclination angle. In sand-laden flows, both the streamwise length and vertical length of very large-scale motions increase with height. It's consistent with the variation law in the clean air flow. The streamwise length scale shows no obvious change compared with that in the clean air flow, while the vertical length scale were reduced. We average the turbulence kinetic energy and the TKE fraction of very large scale motions over the same range of the Reynolds number in the clean air and sand-laden flows. The results show that the particles in sand-laden flows enhance the TKE of very large scale motions, but the TKE fraction of very large scale motions in sand-laden flows is less than that in the clean air flows. Why the TKE of very large scale motions increase but their fraction decrease? We analyzed the total TKE and the TKE for very large scale motions and small scale motions. They are plotted in the in this picture. We can say that all the total TKE and very large scale motion TKE and the TKE of small scale motions increase with sand concentration. However, the TKE increment of small scale motions, the blue circle, are larger compared to the very large scale motion TKE. As a result, results in a decrease of TKE fraction of very large scale motions in sand-laden flows. Here is the contour map of a pre-multiplied spectrum of streamwise velocity. And it can be seen that the peak wavelength, the peak length of the at the long wavelength range does not change in the sand-laden flows compared to the peak length in the clean air. It means that the length scale of very large scale motions is not significantly modulated. Meanwhile, we can also see that the TKE of entire scale motions are enhanced. Comparing to the wavelengths of most energetic structure in the clean air flow, wavelengths of the most energetic structure in the sand-laden flows does not change obviously, as shown in this figure. It means that the length scale of most energetic structure are not influenced by the sand particles. The effect of very large scale motions on the PM10 transport was analyzed as well. The contribution of different frequency components of sand-laden flows to the PM10 streamwise and vertical transportation are shown by the pre-multiplied co-spectrum in the figure. It can be found that the very large scale motions have a substantial contribution to the streamwise PM10 transportation at different heights. An interesting result is revealed in the PM10 vertical transportation. The low frequency very large scale motions provide negative PM10 flux near surface. The reason may be the very large scale motions are mainly low speed coherent structures and leads to less shear stress on the sand surface and less PM10 release. Far from the surface, when the height higher than 2.5 meter, very large scale motions become a significant contributor to the vertical PM10 transportation. By assuming the convection velocity of PM10 is the same as the local streamwise velocity, we can calculate the correlation function for the PM10 concentration. We found that the PM10 concentration shows structural feature. And comparing the length scale of PM10 structure with the turbulence structure, we found that the streamwise length scale for the velocity and PM10 concentration both increase with height. However, near the surface, the streamwise length scale for the PM10 concentration is larger than that of turbulence structures. For higher region, the streamwise length scale for PM10 concentration approximate to the turbulence structure. We also analyzed the correlation of temperature fluctuations to obtain the streamwise length scale of temperature structure. The results show that the length scale of temperature structure increase with height, while they decrease with the strength of vertical heat flux. Finally, here is the summary of this talk. We found the very large scale motions exist both in the clean air and sand-laden flows. The TKE of very large scale motions increase with the sand concentration, while its fraction are decreased. The streamwise length scale of very large scale motions is in sand-laden flows has no obvious change, while the inclination angle increase with sand concentration, and vertical length of the very large scale motions are reduced. We also found the PM10 concentration and the temperature fluctuations shows structure feature. Okay, that's all. Thanks for your attention.
Thank you very much, Guohua. So I have one from Subhathi, who says, interesting talk, which I agree with. First of all, are the streamwise and vertical scales, are they integral scales?
Okay, the streamwise and the vertical length was is not the integral scales. They are estimated by the correlation function with a threshold of RUU or with a threshold of RUU of 0.05.
Right. So they're correlation lengths.
Yes.
Yeah. And the second question he asks is delta the boundary layer height, and how is that estimated?
That's is a very important question. For now, the boundary layer thickness for the atmospheric surface is chosen by ours expression, and we now want to measure the thickness by the LiDAR, and we have bought a LiDAR and put it in the Qingtu Lake observation.
I have a question, if that's okay. My question is that you show that the main change in the turbulent kinetic energy is at the small scales, if I have that right, with sand-laden flow. So do you have a mechanism for why this increase takes place?
For now, we just find the phenomenon, and I don't know why the small scales turbulent kinetic energy is much large, is increased much more than the very large scale motions. I think maybe the sand particles and the size of sand particles and the very large scale motions, their scales has a very large gap. The tiny particles cannot influence the very large scale motions. They maybe they only influence the small scales.
And that's because they're not in sufficient what's the right word, concentration to change, for example, the stratification in any way.
Their change with the concentration. Q is the sand concentration, right. Or yes.